Hello, welcome to 5.7, inverse trigonometric functions. This time we're talking about integration. At 5.6 we talked about differentiation, now it's integration. Okay, so 5.17, theorem 5.17, integrals involving inverse trig functions. Let u be a differentiable function of x, and let a be something positive. Now if you can get it in this form, where it's du over the square root of some constant squared, and the constant squared could be like 5. 5 could be a squared, that's okay. So that means a is square root of 5. Minus u squared, some variable function part, that's going to give us arc sine of u over a plus c. For 2, we have the integral from, integral of du over a squared plus u squared, some constant squared plus some function part squared. That's 1 over a arctangent of, that should be the absolute value of u over a plus c. Integral of du over u times the square root of u squared minus a squared, that's going to give us arc secant. So you're probably thinking, what about arc cosine, arc cotangent, arc cosecant? We left them out. Well, as we talked about in the last section, if you recall, that they're just -1 times these. So that's what I talked about last time as well. When you integrate, we go with just the positive ones. Positive one gives us the arc sine, arc tangent, arc secant. Well, let's go ahead and do example 1 here. Let's just find the integral. So for a, it says integral of 7 over 16 plus x squared. dx. Think of this as 7 times the integral of 1 over 4 squared plus x squared dx. And this fits in with our arctangent. 7 times, it says it's going to be 1 over a, our a is 4, 1 over 4 arctangent of the u, or u is just x in this case, x over 4 plus c. How about b? b has the integral of 1 over x times the square root of 4x squared minus 1. So we have 1 over x times the square root of, think of that as 2x squared minus 1. So in arc secant, this looks like an arc secant that has the variable part subtracted the constant part. Our a is 1 in this case. Our u is 2x. So if I said u equals 2x, our du is going to be 2dx. Don't quite have that 2 there. Also, we're missing something down here, but watch this. What if I took this a step further and said, okay, 2 over 2x, so the 2's would cancel out, times the square root of 2x squared minus 1 dx. So the 2's would cancel, but this 2 dx would be the derivative from 2x. And so our u would be a 2x. So here's our u. u equals the 2x, as I just said. So we end up with 1 over u times the square root of u squared minus 1 du. This is the du. And this will give us our arc secant. So it's going to be 1 over 1, because the a is 1, arc secant of u, which is our 2x absolute value, over 1 plus c. So that's going to be arc secant absolute value of 2x plus c. And for part c, we have the integral of t over the square root of 1 minus t squared dt. This should have been t to the 4th. So change that, it's t to the 4th. Otherwise, this is not the way we can do this. So if we say u equals t squared, du is going to be 2t dt. And we can treat this as 1/2 integral of 2t over square root of 1 minus t squared squared dt. So we have our 2t dt, and we have 1 minus t squared squared, so that's our square root of 1 minus u squared. So this is going to be the arc sine. the 1/2 from out front here, arc sine of t squared plus c. Again, the 1/2 of 2 is just 1, so we get back to what we started with. And go on to page 2. Feel free to pause that if you'd like. Okay, it says find the integral. We have x minus 2. The integral of x minus 2 over x plus 1 squared minus, or plus 4. Now, given that we have something squared, a variable part squared plus 4, this looks a lot like our arctangent. Stuff on top doesn't quite look like it, so we can work with this a little bit. Okay, so we have x minus 2 over, if we expand this out, we have x squared plus 2x plus 1 plus 4. This is the integral of x minus 2 over x squared plus 2x plus 5 dx. So if our u equals x squared plus 2x plus 5, the du would be 2x plus 2 dx, excuse me. And we have x minus 2. What we can do with that is to try to make this appear as 2x plus 2. So if we said 1/2 integral of 2 times 2x minus 2 over x squared plus 2x plus 5 dx, that would be 1/2 integral of, sorry, that's not a 2 here, it's just x, 2x minus 4 over x squared plus 2x plus 5 dx. So again, my goal is to make this look like 2x plus 2. Take this a step further. We have 1/2 integral of 2x minus 4 plus 6 minus 6. Why plus 6? Because negative 4 plus 6 gives me a positive 2. This is 1/2 integral of 2x plus 2 minus 6 over x squared plus 2x plus 5 dx. Now we can split that numerator and we'd have 1/2 integral of 2x plus 2 over x squared plus 2x plus 5 dx, where this is the derivative of that, plus 1/2 integral of negative 6 over x squared plus 2x plus 5 dx. So in the first case, we have 1/2 integral of 1 over u du. And the second case, I'm going to do minus 1/2 times 6. Why minus? Because the negative 6 integral of 1 over, and we had this factor in the beginning, let's go back to that, x plus 1 squared plus 4. So that this first part is going to be 1/2 natural log of the absolute value of u plus, or I should say minus 3 times. Now we have our arctangent. This arctangent will become 1 over 4 arctangent of x plus 1 over 4, that absolute value, plus some c. So we have 1/2 natural log of the absolute value of x squared plus 2x plus 5 minus, like I'm missing, am I missing anything? Oh yes, I am. First of all, 4 is 2 squared, so this should have been a 2 here and a 2 over here. I apologize for that. So there we go, minus 3/2 arctangent of the absolute value of x plus 1 over 2 plus c. That was kind of fun. The idea then is we were able to make it into a U substitution for part of it, and then the rest of it we were able to make it into an arctangent. Let's go on to example 3. On a first glance, example 3, I see a radical. My first thought was, very preliminary, was, oh, I have something outside the radical. Oh, maybe this is a secant. But whenever I see it's 1 minus, it's a constant minus the variable, it's going to have to go towards the sign, arc sign. Now this, if I said my u equals the square root of x, then my du is going to be 1/2 times 1 over the square root of x dx, because the derivative of square root of x is 1 over 2 times 1 over the square root of x. So I don't quite have that, but I'm close. So I could say 2 times the integral of 1 over 2 times the square root of x times the square root of 1 minus x. Now I have this 2 square root of x is the derivative of the stuff in here. So I can do my sine part. This becomes 2 times arc sine of square root of x plus c. That's it. I kicked a marker away by accident. Now, just to give you a reminder of completing the square, when I pretty much every time I teach completing the square in pre-calculus, I get people just so angry with me. Why do you make me learn this? How horrible are you? What a bad person, you make me learn this. This is so difficult. Who on earth would make someone learn this? I'm like, well, there's going to be a time where you're going to need it. And here's an example of that. We're going to be talking about in here where we have to have that skill down. So if you're not strong on that, if you're one of the people who sent me lots of mean emails, then this is the time to brush up the skills on this. X squared plus bx plus c would be x squared plus bx plus b over 2 squared, then minus b over 2 squared. You add and subtract the plus c. So this becomes a perfect square trinomial, and then this is the constant part that's left over. We're going to have to be able to do that now. Okay. So, in this one we have the integral from -2 to 2 of x squared plus 4x plus some blank minus the same blank plus 13. That's the integral from -2 to 2 of, I'm going to say 1 over x squared plus 4x plus, now what's half of 4? Half of 4 is 2. 2 squared is 4. So plus 4 minus 4 plus 13 dx. Now we have our perfect square here. That's going to be 1 over x plus 2 squared plus 9. So in this case we have the sum of 2 terms in the denominator. That looks like it's going to be an arctangent. So this would become 1/3, because at 9 square root of 9 is 3, 1/3 arctangent of x plus 2 over 3 from -2 to 2. That's 1/3 arctangent of 2 plus 2 is 4/3 minus 1/3 arctangent of -2 plus 2 is 0. we have 1/3 arctangent of 4/3 minus 0. That's our answer, 1/3 arctangent of 4/3. Okay, moving along here. Feel free to pause that one. Going on to page 3. We have another integral, surprisingly, given that this is a chapter of integrals, of the square root of 4 minus x squared dx. That one looks pretty straightforward. Where my a is 2 and my u is just x. So this will become, and I have 2 dx's, so that's a mistake. Equals arc sine of x over 2 from 0 to 1. That's arc sine of 1/2 minus arc sine of 0. Arc sine of 1/2 is pi over 6 minus 0 is pi over 6. Now page 385 has a current 385 has a list of current integration formulas, the ones we've gone over so far. So let's say these are current, and there are ones we have not encountered. There are a bunch. I have a book. I have a couple of books, thick books, full of integration tables. So there are a lot of them out there. Okay, example 6. It says use the specified substitution to find or evaluate the integral. It tells us use u equals the square root of x minus 2. That means that u squared would be x minus 2. Now in the denominator I have x plus 1. Oh, by the way, the derivative here would be 2u du equals dx. So that's, what's our u in this case? This is our u. That's u. We'd have, this gives us the integral of u over we have x plus 1 and u squared plus 2 is equal to x. So what we have is u squared plus 2 plus 1 because our x is u squared plus 2. And our dx is 2u du. Okay, got enough u's in there now? Can't spell substitution without u. Okay, let's see. We have the integral of 2u squared over u squared plus 3 du. Now notice if I take this next step, watch. Got to be creative sometimes. If I add 6 and subtract 6, I really added nothing to the numerator. Now, notice by adding 6, this makes 2u squared plus 6 is double what we have down below. So we have 2 times u squared plus 3 over u squared plus 3 du minus the integral of 6 over u squared plus 3 du. So in the first case, I just end up with the integral of 2 du minus, in the second case, 6 times integral of 1 over u squared plus 3 du. This looks like an arctangent. So we have 2u minus 6 times, now arctangent, it's going to be 1 over a is square root of 3, so it's 1 over the square root of 3 arctangent of u over the square root of 3 plus c. This becomes 2 times the square root of x minus 2 from here, minus, now 6 divided by the square root of 3 is 2 times the square root of 3 arctangent of the square root of x minus 2 over square root of 3 plus c. And that's the end of that problem. So you really had to be creative and try to, what we did was create something that looks like this down below. I mean, looks like it's double. So that can cancel out. Okay, feel free to pause that one if you need some more time. I'm going to go on to example 7. Example 7 says use the differential equation and the specified initial condition to find y dy dx is 1 over 4 plus x squared. So that means y is going to be the integral of 1 over 4 plus x squared dx. And that's going to be an arctangent. So that's going to be 1/2 arctan of x over 2 plus some constant c. Now y of 2 is equal to 1/2 arctangent of 2 over 2 plus c, and that's pi. So 1/2 arctangent of 1 plus c is pi. So 1/2 arctangent of 1 is going to be pi over 4 plus c is pi. So it's pi over 8 plus c is pi. So c is 7 pi over 8. And y equals 1/2 arctangent of x over 2 plus 7 pi over 8. Okay, we've got one page to go and one example to go. And this finishes chapter 5. This from the textbook, it's number 64, I believe. It says a differential equation, a point, and a slope field are given. So this is called a slope field. It's a slope of the function at any given point. Slope of the function. So you take the derivative and plug in the ordered pair and you get the slope. And this looks all horizontal, but if you plug in some values, you get some lines here. Here's the differential equation, here's the point. So 0, 2 is our point. Looks like it's scaled to be there. So sketch two approximate solutions of the differential equation on the slope field, one of which passes through the given point. And that's this one here. Here's one, and here's another one down here through the origin. So two solutions on the slope field. Use integration to find the particular solution of the differential equation, and use a graphing utility to graph the solution. Compare the result of the sketches in Part A. Okay, so Part B says we have y prime equals 2 over 9 plus x squared, what we're seeing right here. So y would be the integral of 2 over 9 plus x squared dx. And it might be helpful to see this as 2 times the integral of 1 over 3 squared plus x squared dx. And of course, everyone say it with me, that is a what? An arc what? Tangent. Good job. So y would be equal to 2 times 1/3, why 1/3? Because our a is 3, arctangent of x over 3 plus some constant c. Now, y of 0, if I plug in 0 for x, I'm going to get 2 for y, is 2/3 arctangent of 0/3 plus c, and that is 2. So 2/3 arctangent of 0 is 0, plus c is 2, so c equals 2. And our particular solution, y equals 2/3 arctangent of x over 3 plus 2. And that does it. I'm going to scroll this up to show you the solution graph. That's the graph of the solution. And so notice how this graph here looks remarkably similar to the other graph there. So this is off the slope field, and the other one's just graphing the graph. Okay, well, I hope you like this section. I hope you like this chapter. You know, we're using some more of these tools, learning some new tools and using them. But we're really using the tools of differentiation and integration. Great stuff. Okay, send me your questions. Let me know if you have any.